welcome to my presentation. My talk will be about the investigation of effects on the structural, optical, and gas sensing properties of Erwere-doped zinc oxide and zinc oxide nanorods. This is the collaboration between three universities. These universities are Gazi University, is the Kastamonu University, and the Bahcesehir University. This is the out of the scope. It's a different area, okay? The first. Oh my God, it's not working. Yeah. What is the motivation and for this work? Zinc oxide materials and zinc oxide based nanomaterials such as nanoparticles, nanorods, nanothin films can be used in many fields because zinc oxide is a multi-purpose materials and it is used in gas sensors, conducting windows, varistors, transparent electronics, spintronics, optoelectronic devices. However, the defects that occur during growth in these nano-sized material are still an incomplete issue. That's why it is not used effectively. What is the aim of this present work? We divided this present work in the two parts. First, we investigated zinc oxide nanorods, temperature and the growth time to find the better crystalline materials. After that, we investigate the role of the defect on the structural, optical, and the gas sensing properties of the zinc oxide nanorods. This is the schematic diagram of the production process of zinc oxide nanorods. We can produce zinc oxide nanorods. It's just nanorods, and the second one on the seed layer on the thin films, nanorod like the brush. How we can do this? Okay, if you want to produce just nanorods, we can use hydrothermal routes and directly after the heat treatment is 90 degrees with the different heat treatments and the growth time, we can produce nanorods. The second one is on the nanorods. It's on the thin films nanorods. It's okay like this. First, we have to clean. It's a substrate. It's a glass or the silicium substrates. We use glass substrates. And after that, it's a dipping on the solution and the coating zinc oxide. It's a seed layer. Then use a zinc oxide. It's a precursor material. And after that, use a heat treatment and produce on the seed layer zinc oxide nanorods. When we produce zinc oxide nanorods, the first key question is result material is the single phase or not. This is very important. If it is not single phase, then that means you cannot understand that the properties comes from the single phase or the second phase. That's why we use XRD to check it is a single phase, but it is not enough. We need to check with the Rietveld refinement method also. Look at these results are from the XRD. There is only single as a peak. This is the C direction peak, and this is the single phase. Also, we check with the Rietveld refinement method. This, and of course, crystallographic parameters and the grain size of zinc oxide nanorods obtained from the diffraction pattern. This is the table. and we calculated the C lattice parameter, green size, strays, and other properties here. We calculated diameter length of the nanorods, aspect ratio of zinc oxide nanorods, different growth times and the temperature. This is the result of the scanning electron microscope from the top surface with for the different temperature and the growth time. I didn't put here, and there is the cross section, but I will move a little bit down. I'm sorry, because this is the, oh my God, where is this? Yeah, look at here. This is the cross section. I forgot to put the above this. Look at the cross section. There is the nanorods on the seed layers. Again, I'm sorry. Okay, I will back very fast. That means I came here. You can see it's a hexagonal nanorods here. After that, we check that is it zinc oxide nanorods or not. This is the EDX mapping images. Okay. And after that, this is the characterization of the nanorods. And after this point, we continue with the optical properties. And we take transmittance of the nanorods, and we calculate using tau plot. It's a band gap. Result, I will show you at the table. Okay, that means transmittance decreases with increasing growth time, also decreasing with increasing temperature, entering temperature, and the band gap is the opposite. No, it's the same. That means when increasing the growth time, it's also band gap decreases. When we increase it, it's temperature, also band gap decreases. After that, it is very important to check defects on the material. Maybe it's right now it's to check is a defect acting on the application. It's very important, and this is the PL measurement results. There is two emission. The first one is the near bound emission, and the second one is the deep level emission. Deep level emission is the visible regions that from the first emission we can check that the crystallinity of the nanorods. From the second emission we can check defects time, but when we take this we cannot understand that sub peaks there. That's why we use physics program to check the Gaussian decomposition. Look at after it's this procedure, we found it's 9 sub peaks, and the first and the second peaks are for the near bound emission, and I did a mistake, I think. Okay. Okay. Can I move it? Okay. This. Okay. There are 9 peaks, okay? 2 of them are for the near bound emission, and the other peaks are for the defect types. And as a result, this is for the growth temperature. As a result, with an increase in the growth time, the double charged oxygen vacancies, it is a donor, decreases, whereas oxygen interstitial acceptor increases, however, growth temperature decreases as a double charged oxygen and interstitial oxygen increases. Okay. As a result, we can say that zinc oxide nanorods can be grown according to the DEFECTS, donor or acceptor, by selecting the appropriate growth time and temperature depending on the place of use. That means we found that it's using different temperature and growth time, we can change that the DEFECTS. This is the conclusion. What's the important point I say to you, that's why I will pass this slide. Then, another important point is I showed that the zinc oxide nanorod is we change its annealing temperature and the growth time. Then we doped zinc oxide nanorod with the rare earth element. Of course, we use its metals, transmission metals, and we published many articles using this. That means our goal is when we doped with the rare earth elements to sense some gases and correlate with the defects. I will show some results, but this study is right now ongoing. That's why we have not correlation between defect and the gas sensing properties. Just I will show you some results, okay? That means we doped the erbium with the nanorods. Again, we found it's from the XRD results phase of the erbium doped zinc oxide nanorods. It is very important when we dope the nanorod with the second element, it is very hard. That means to find changing the second element with the zinc oxide nanorods, zinc oxide is a place. This is the top surface scanning electron microscope, and the other one is a cross section. This is the EGS, and from the EGS we can see is an erbium element here. That means we doped successfully. This is the average radius of the nanorods, increasing erbium doped zinc oxide. After that, again, we take a transmittance, okay, and also we calculated its band gap. From this side, I think I put two of them. That we can see that when we increase the doping ratio, transmitted decreases. Also, band gap. This is the green one, and the purple. That means band gap decreases too. Again, to understand the defect for fabrication erbium doping nanorods, it's again we took PL measurements, and again we use the Fittig program with the Fittig program Gaussian decomposition, and we found the defects. Last part is we use carbon dioxide sensing. This is sensitivity versus temperature. This is the sensitivity with the different flowing. It's a carbon dioxide gas, and the time. And again, this is another one. And this is the comparison of sensitivity response time and the response time at the 100 ppm gas concentration. Right now, I told you that we are ongoing this project. That means there isn't right now correlation with the gas sensing properties with the defects. Okay, thank you so much. Many thanks to the Bahcesehir University, Gazi University, and the Kastamonu University in Turkey.
Yeah, thank you, Lutfi. We have now time for questions.
because...
Yes, please.
Yeah.
I missed when you prepare
So
your
wait a
sample.
second for the microphone so
Sorry.
people
I'm
online
sorry.
can follow. Yeah,
Yes.
thank you.
When you prepare your samples for X-ray diffraction, do you remove the rods from the substrate, or it's all together?
We prepare two different nanorods. It's just nanorods, and the other one is on the seed layers. That means we first, took XRD with the nanorods, just nanorods, and then we try to use with the substrate and the seed layer and the nanorods. Because the seed layer is a zinc oxide, that's why I prefer first one.
Yes, also because you're using a Rietveld method.
Yeah, just we have two different samples. Okay.
Okay, thank you.
You're welcome.
Yeah, what does said the type of gases that you could sense with these zinc oxide nanorods? So what is the physics that
It's the gas sensing is like the sensors. It's like we use is a nanorod is a metal oxide. It's sensors. That's why it's sensitivity to the gas. Different gas humidity is a carbon dioxide and the like.
Okay, thank you. So if there are no more questions in the room, so we move to the coffee break. So we now have 10 minutes for coffee, and we see in the next session.
Thank you so much.
Thank you again for the talk, and let's